Hello and welcome to this. This actually turns out to be part two of our series in Lagrange's theorem. So this is really entitled just exploration, right? This is the second part of our exploration into Lagrange's theorem. Lagrange, Lagrange's theorem, right? So Lagrange was some French mathematician, right? That's at least according to what we know. So, and the name kind of sounds French. Lagrange. Lagrange. Okay, well, Lagrange's theorem talks about this idea. Suppose we have G, right? So, suppose we have G here, right? So, this is G, and we are saying that G is finite, right? So, suppose G is some finite group, okay? Now, let H be a subgroup of G, right? So we're going to call this H. So the notation for that is we're saying H is a subgroup of G, right? Now, of course, we've mentioned a lot here that H, when we say subgroup, we just mean H is a subset of G, right? H is a subset of G that is also a group, right? Now, the question arises, well, I mean, if G is finite, then any subset of it must be finite. So H must be finite as well, right? So the question becomes, well, if we consider the order of H, right, and the order of G, what's the relationship between them? In particular, does the order of H divide the order of G necessarily, right? That's the question. Is this true? Does the order of H divide the order of G? And this is really what Lagrange's theorem is all about. So let's think about, so in the first video into this exploration of Lagrange's theorem, this is exploration 2, right? So in the first exploration of this theorem, we're still trying to establish this question still, right? How does the order of H divide the order of G? And our strategy was as follows. We're saying, look, in order to decide whether the order of H divides the order of G, one strategy we can use is to study H in relation to G. And then, in particular, we're going to study H in terms of these things we're calling cosets. For instance, left coset is something like GH. We take some little G element of big G, right? So the strategy was, well, we take some little G that's an element of big G, okay? Then we multiply to the left by H, and this thing we're calling a left coset. So for instance, if H were equal to, let's say, H1, right? These are the elements of big H, H2, H3, all the way up to, let's say, HK, right? So suppose this is what we had. This is H sub K, right? Natural question, well, what is GH? GH is exactly what we think it is. It's multiplying H by G to the left. So the end result would just be, well, we guessed it, G times H1, G times H2, right, dot dot dot, G times HK, right? So this is what GH is, and the idea was maybe if we study GH, right, if we study this left coset of H, if we study GH, maybe that will give us insights into what the order of H is, what is the size of H, kind of compared to the size of G, compared with the size of big G. Right? What's the ratio between the cardinalities? And part of the intuition for why this would work is because, well, if we look at GH, now we notice that actually we're going to find out that the elements of GH, that is the cardinality of GH, is precisely the cardinality of H, right? This is something we're going to discover soon. And if the cardinality of GH is precisely the cardinality of H, then it means if we study the order of GH, we're also studying the order of H. And so if we study the order of GH and know how GH relates to G, then we may have some idea about how maybe the cardinality of H is related to the cardinality of G. Right? So that's kind of the big picture here. And so far in the last video we learned a few things. We learned that, for instance, GH in general, the left coset GH is not necessarily a group. I mean, H is a subgroup of G, we know that. Because H is a subgroup of G, we know G is a we know that H is a group. But we never said that GH is necessarily a group. And the trivial idea we used was the following. Well, suppose we have our group G and we pick H to be a subgroup of G that's just the identity element, right? So we note that the group consisting of, if we pick only the identity element, H actually turns out to be a group. Inverses, closure, one can check that this is true. And the end result of this is that, well, so this H, which is just the identity element, is a legitimate subgroup of any group G. Now let's look at the coset. GH turns out to give us just G, right? That's what it do. G times the identity is just G. So now notice, how can GH, this coset here, how can it possibly be a subgroup? Because a subgroup must be a group. And this thing is certainly not a group, right? Because G, well, G is not even the identity element. So for something to be a group, there must be an identity. And G was chosen. Now, this G is an element of G, and in particular, we've chosen G to not be the identity element. So in which case, GH will give us some set that has no identity element. And if it has no identity element, it can't be a group. So what we concluded last time was that GH, the left coset GH, is not necessarily a group. Right? But this still triggered our curiosity, and we were now pushed to ask the question, well, okay, fine. In general, GH, the left coset GH, is not necessarily a group. But still, under what conditions is GH a group? And our investigations led us to the following idea, that if G is an element of H, right? So remember, G has to just be an element of the group. Little g has to be an element of the big group G. But I mean, since H is a subgroup of G, well, H is a subset of G, which means that little g could be an element of H. And here's what we established before. If little g is an element of H, then that implies that GH, the left coset GH, is actually a group. In fact, it's a subgroup of G. Right? We realized this. The other thing we realized was that we also saw that, look, if GH, if the left coset GH is actually a group, if it's, let's say, some subgroup of G, it means if it's a group, then the following also holds. It is also true that G is an element of H. So the end result of combining these two statements gave us the following idea, a complete criterion for determining whether a coset is a group or not. We came to the following conclusion. GH is a, so GH, the left coset GH is a subgroup of G if and only if G is an element of H. Right? That was the result we came to. Well, why is this result important? Well, part of the exciting thing about this result is that it tells us that if we ever want to find out whether some coset GH is a group, all we need to check is if G is an element of G. The other thing it's telling us is if we ever want to guarantee that GH is a group, all we need to do is to pick G to be an element of H. Right? The other conclusion we came to was the following, that if G is an element of H, then GH equals to H. We came to this conclusion. Right? And the reason was, look, if G is an element of H, and let's say H equals to H1, H2, all the way to, let's say, HK, alright? GH, right, remember we were saying G is an element of H. GH will just be, well, G times H1, G times H2, all the way till G times HK, right? Now we noted something here. We noted that, look, G times H1, okay, since G is an element of H and H1 is an element of H, well, one thing we realize is that since H is a subgroup, it's also a group, so it's closed. So GH1 is an element of H. GH2 is an element of H. In fact, all these elements are elements of H. The other thing we established also was that for any Hi and Hj elements of H, Ghi never equals to G sub Hj, say, where Hi and Hj are being taken to be elements of H. We established that this is not true if Hi does not equal to hj. Right? This can never happen, right? So if hi does not equal to hj, ghi can never equal to ghj, which means that all of these elements are distinct, right? And how many elements are there? Well, their cardinality of h elements, right? In cardinality of their cardinality of h elements, well, in h, right? Of course, by definition, and gh is, since each of these elements are distinct, and we have cardinality of h of them, there are as many elements here as there are elements of h. So we came to this conclusion as well, that cardinality of h equals the cardinality of gh, right? Okay. And so if this is true, right, and we're saying now we have as many elements in the coset gh as there are elements in h. The other thing we also have is that, well, every element in this gh, coset gh, is an element of h. Well, what possible conclusion can we draw from this? The conclusion becomes clear. Gh must be equal to h. Right? So that's a nice thing, again, we're learning about cosets is, well, if we ever pick an element little h in h, and we're wondering, well, what coset does h give us? That automatically gives us h. Right? Now we know that we know that identity. So writing h is kind of a waste of time. We just need to write h here, right? And so this gives us some other interesting property of these left cosets. In this, we could do left or right, but in this case, the mathematicians typically like to work with the left coset instead. But so this is one other idea we're getting. But in particular, I guess another important thing to note is that, look, here we said if G is an element of G, if G is an element, if little g is an element of H, then GH, size of GH, is the same as the size of H. Okay, that's what we established. But notice, natural question is, well, what if G is just an element of G, not necessarily an element of H? Is it also true that GH, cardinality of GH equals to H? Right? Is this true? Well, it turns out that it is true, but it's up to you to try and figure out why this is true. The argument is pretty similar to what we've been doing before. That is, if G is an element of G, not necessarily an element of H, is the cardinality of GH always equals the cardinality of H? So this statement actually turns out to be true, but it's up to you to actually verify and prove that is true. Okay. So we're learning a lot about these cosets, right? So one thing we've come to the conclusion to that is, if G is an element of G, right, just for any G element of G, the coset GH has the same size as H. Okay. That's an interesting realization, right? It means that if we want to, because our overall goal, recall, is to find what's the relationship between the cardinality of H and the cardinality of G. That's our relationship here. In fact, when I figure out if cardinality of H divides the cardinality of G, that's what Lagrange's theorem talks about. But notice, if GH always has the same cardinality as H, we might as well figure out, well, what's the relationship between the cardinality of H, of GH, these cosets, and the cardinality of G. For instance, if we found out that the cardinality of these cosets divides the cardinality of G, then we'd know also the cardinality of H divides the cardinality of G, because ultimately cardinality of GH is the same as the cardinality of H, right? We just established that here. Okay. So these cosets are turning out to be pretty interesting. Well, what else? What else can we realize? So it turns out that a natural question to wonder about is, well, suppose that we found out that, let's say just for funsies, suppose we came to the following conclusion, that the cardinality of GH, every coset, divides the cardinality of G, right? Suppose we came to this conclusion somewhere. We haven't come to this conclusion yet, but suppose we did. What would that tell us? Well, what does it mean for one thing to divide another in real life, right? So, in real life, as if this is fake life. Okay, let's say we have the number 6, all right? 6. when we say that 3 divides 2, 3 divides 6, what do we mean? Well, one interpretation is that 3 times 2 equals to 6, right? But another one is exactly what it sounds like, 3 divides 6. That is, if let's say we had 6 boxes right here. If we had 1 box, 2 boxes, 3 boxes, 4 boxes, these are a total of 6. 1, 2, 3, 4, 5, 6. Okay. To say that 3 divides 6 means that we could get 6 and break it up into groups of 3, right, without overlap. So this would be this group of 3 combined with this other group of 3 of the 3 boxes over here. So we have these 3 boxes and the other 3 boxes on this side, right? These other 3 boxes. When we get these 3 boxes and put them together, we end up with 6, right? That's one interpretation of what 3 divides 6. That is, 3, this collection of 3 boxes partitions the collection of 6 boxes. And so, a natural question is, when we say that the cardinality of GH, let's suppose that we're saying that the cardinality of GH divides the cardinality of G. What would that mean? Would it mean somehow that GH partitions G? So in the same vein, would we have something of this nature? Would we have this? We have some group G. Let's say we start from here. We have some group G. Okay. So this is a group G. All right. And then maybe, just as before, maybe we break it up. Like we have GH, right? That's all the elements of H multiplied by G. Right. So maybe a better way to think about it is, okay, let's suppose that, just for fun, let's suppose that, do we want to do this or not? Sure. Why not? Let's suppose that H equals to, let's say it has just 3 elements or whatever. Let's say it has elements H1. No, what the heck? We're doing mathematics. We might as well be general. So let's say we have up to HK. Okay. That's our current setup, right? So H is the group and it has K elements in it. Okay. So if we said that cardinality of GH, the left coset, divides cardinality of G, what would that, could that somehow be interpreted just as before here we said, look, if 3 divides 6, then part of what we're saying is that 6 can be partitioned into groups of 3. Well, if we thought about cardinality of GH dividing cardinality of G, are we kind of saying that GH partitions G? Do the cosets partition G? And what would that mean? Perhaps maybe, like, if we picked, maybe we can find elements G1. Let's break this up into maybe 4 pieces. What the heck? Let's say 4 pieces. Perhaps maybe we can find elements G1, G2, G3, G4, and have the following property that, for instance, G1 times H1, G2 times H2, dot dot dot, sorry, this is still G1. G1 times HK, right? What is this? Well, this is just the coset GH, pretty clear, G1H, where with the element, these are all taken to be elements of G, by the way. G1, G2, G3 elements of G, right? And let's say maybe we partition this. Let's not call this G2H1, G3H1, sorry, G2 again, we're getting confused, H2. Let's say we go up to G2HK, alright? And then here, right, what is this? Well, this just turns out to be G2 times H, right? Our left coset formed by G2. Well, how about this? This is now G3H1. Let's say this is G4, G3H2, and let's say we go to G3HK. What is this? Well, that's just our coset G3H. Alright, how about here? Now we have G4H1, G4H2, all the way till G4HK. So right here we now have G4H, and that's our other coset. So, right, so is it possible for us to partition the group G in terms of these cosets like this, right? So let's say it turns out, right, obviously, like, for this partition to work, there can't be overlap. For instance, well, perhaps it's best to do this using an example. Let's find a group that's easy to work with. What would be an example of a really nice group to work with? Sure. So we need a group and a subgroup. Okay. One that's not gonna make our lives extremely hard. So let's see. Let's pick an actual group just to see, maybe to try and visualize some relationship between the cosets GH and a group G. All right. So what group are we going to work with? Maybe the dihedral group. We could do that. Um, what's a nice group to work with? Well, that's a good question. Well, fine. Why not? Let's work with the dihedral group. Because it's hard to think of a group that's much easier to work with. Um, okay, I mean we could do dihedral. Those are some of our examples of good groups to work with. We have dihedral group. Um, we have, well, should we do this or not? Well, okay. Now this gets confusing. Or maybe let's try something simpler. Okay. So let's start with the group G equals to Z. Right? That's the set of integers. Right? We have the group G set of integers, and then we're gonna pick some. Uh, we're gonna try and evaluate cosets of this. So for instance, well, right, Z, right, set of integers. So we start from 1 and minus 1. Okay, we start from 0, then 1 and minus 1, 2 and minus 2, 3 and minus 3, etc. Right? That's our group of integers. Right? It turns out to be a group under addition. That's pretty clear, isn't it? So if there's still confusion, please let's try and check to see that G, if we set G equal to the set of integers, Z plus this group, the set of integers under addition forms a group. And so a natural question to ask is, well, maybe we can form some cosets out of this, right? In particular, let's pick the set of, what are we going to pick? Um, Integers again, positive integers perhaps. Um, let's see. Okay, let's try this. So we have Z, right? Z is the set of integers, right? We've said that, and that can be verified, that this is actually a group under addition, right? So there we go. We have a set of integers right there, okay? Now, is it true that, let's try 4z? How about 4z? What's 4z? Well, 4z is just going to be all the elements of z multiplied by 4, right? So that would give us 0, 4, minus 4, what, 8, minus 8, 12, minus 12, right? So, well, first of all, is 4z a group, right? And what would it take to check that 4z is a group? Well, just the usual properties. Is there the identity? Yes. But is it a group under addition? Well, the identity is 0, right? That's clear. Um, do elements have inverses? Yeah, sure. If we get any element of 4z is of the form 4n, where n is some integer. So does the inverse of 4n exist? Sure. Negative 4n exists. 4n plus negative 4n gives us the identity. So inverses exist. Associativity exists because associativity, we're dealing with addition of integers, and that's associative. Okay. Closure? Sure. If we got some multiple of n and added it to some other multiple of n, do we still get a multiple of n? Turns out that we do. Just factorize. N plus m is still an integer, so indeed, it's closed. So what we have here is actually 4z is actually a group. And since 4z is a subset of z, we have to come to the following conclusion. 4z is a subgroup of z. Right? So before we're analyzing the following, we're talking about these kinds of scenarios. We have a group G. We want to actually visualize a coset here. We have a group G, and we're talking about a subgroup of H. Okay. So now we've set up an analogous situation here. So let's do this side by side to make it much more clearer. So now what we've had is our group G now is Z. Right? Z is our group G, and we've found that we have this subset of G called, sorry, this subgroup of Z called 4Z. All the integers multiplied by 4. Okay, so, well, what do the cosets look like? Okay, so what did we define cosets to be? We said that, look, if G is a group under, say, some operation dot, right, all right, then the coset, left coset GH would just be, well, we pick some element little g in big G, and GH would just be, we'll write it like this, GH, like that, and GH will just be the coset, well, what would it be? It would be, well, G times H1, G times H2, where the HI's are, these H's are elements of big H, and maybe GHK, supposing it has HK elements. Those were the left cosets. Okay, well, what's the analog over here? Well, over here we had the group G under dot, right? This sort of multiplication which we're writing as dot. But here we have the group Z under addition, right? So what's the coset going to look like? Well, here we picked an element G in the group, right? So in this case we're going to have to pick some element G in the group Z. Well, just some integer. For instance, we can pick the integer 1, okay? We start with 1. If we pick 1, we notice the following. I mean, let's start with 0. What the heck? Let's start with 0. We could pick the integer 0 in Z, right? Well, what's ZH? Z, in this case, it was GH. So what's this going to be? It's G times the operation. So in this case, our operation is addition. So our coset is going to be 0 plus whatever the subgroup is, 4Z. 0 plus 4Z. That turns out to be a coset, right? In this case, here we're dealing with the dot, here we're dealing with the plus, right? That's our notation. Let's write it well, just to make sure we don't end up confusing ourselves. So there we go. Now here we have 0 4z, right? So we have 0 plus 4z. Okay, well, 0 plus 4z just turns out to be what? Well, it will be over here, G times H turned out to be, well, we get every element of G and multiply it by H. Okay, so we get every element of H and multiply it to the left by G. So H1, H2, HK multiplied to the left by G. Okay, so over here our multiplication is addition. So the end result is, well, we'll get every element of 4Z and add 0 to it. Right, so now we'd have, so remember 4Z was just 0, 4, negative 4, 8, negative 8, 12, negative 12. So 0 plus 4z will be 0 plus, well, the first element of 4z is just 0, right? So 0 plus 0. The other element of 4z is going to be, well, 4. So 0 plus 4 right there. Then 0 plus negative 4, okay? And then 0 plus the next multiple of 4, which is 8. 0 plus negative 8, and so on and so forth, right? This coset is infinite. All right. Okay. That's 0 plus 4z, right? And obviously that just turns out to be what? 0 plus anything is 0. So 0 plus 4z is really just 4z, right? The zeros give us the same set back. Well, okay. Let's pick some other element of z. Well, let's pick 1. 1. Well, the left coset is going to be 1 plus 4z. Okay, so what's 1 plus 0? Well, that'll give us just 1 plus 0, 1 plus 4, 1 minus 4, 1 plus 8, 1 minus 8, etc., etc., right? That's what 1 plus 4z will look like, right? It's an infinite process, okay? Let's look at another coset, 2 plus 4z. Okay, all right. What's 2 plus 4z going to be? Well, just 2 plus 0, 2 plus 4, 2 minus 4, blah, 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 okay? We get the story here. And 3 plus 4z would give us what? Well, actually, it's better to write them out. Let's write these things out, Why not? No. There's this Swahili proverb that talks about, says, if you say it, it's umemla ng'ombe mzima usishinde na mkia, which means you've eaten a whole cow. Don't fail to eat the tail. Right? The idea, we've done all this work, all this work. Why stop now? Let's write everything down correctly, right? That's the idea. Okay. Why did the Swahili proverb come into this? God only knows. All right. So 2 plus minus 4, 2 plus 8, 2 minus 8, 2 plus minus 8 actually. So yeah, and then we keep going, right? That's what we have here. Okay. Let's look at 3 plus 4z. Well, what's that's going to give us? That's going to give us what? 3 plus 0, 3 plus 4, 3 plus minus 4, 3 plus 8, 3 minus 8, and so on and so forth. All right. Okay. Let's do one more for funsies. Okay, let's do two more. What's 4 plus 4z going to be? Well, 4 plus 4z is still going to give us, well, now we'd have, well, 4 plus 0, 4 plus 4, 4 minus 4, 4 plus 8, 4 minus 8, and so on and so forth. Okay? And then, well, what's 4 plus 5z going to give us? Well, 4 plus 5z is really just going to give us 4 plus, oh, sorry, now it's going to be 5, right? 5 plus 0, 5 plus 4, 5 minus 4, 5 plus 8, 5 minus 8, and so on and so forth. All right. Actually, no, it's probably going to be perfect for us if we, well, this was 5. This is supposed to be 5 plus 5z. It's going to be perfect for us if we do two more of this. So let's do that. What's 6 plus 5z? Well, 6 plus 5z is just 6 plus 0, 6 plus 4, 6 minus 4, 6 plus 8, 6 minus 8, and so on and so forth. And the final one here is 7 plus 5z. What does that give us? Well, 7 plus 0, 7 plus 4, 7 minus 4, 7 plus 8, 7 minus 8, and so on and so forth. Alright, so this is really the setup we now have, right? So these are just some of the cosets, right? There seem to be many of them. These seem to be just some of the cosets of when we look at Z as a group, take H as a subgroup of it. In this case, 4Z is being viewed as a subgroup of Z, which it actually is under addition. And then we consider what the left cosets are going to be. 0, the left coset formed by 1, by 2, by 3, by 4, etc. Okay, so I guess first question is, are there really infinitely many cosets here? Right? For instance, if we look at 0, what does 0 plus 4z give us? It just gives us 4z back, right? It gives us 0, 4, minus 4, 8, minus 8. So this is just 4z. 0 plus 4z we saw was 4z, right? Let's look at 4 plus 4z. Well, 4 plus 4z still gives us 4, 8, right? 4, 8. It's going to give us, what else? 4, 8. It will give us 0 back. 4 plus, okay, so maybe, okay, so here's what we're saying. Well, we've done all this work. Okay, should we go to the left or to the right? Yeah, let's. Right, so, okay, here's what we've established so far. We've established that 0 plus 4z, okay, 0 plus 4z is just equal to 4z. Right? It kind of makes sense. All right, so this is our realization here. 0 plus 4z is just 0 plus 4z is just 4z. Right? What about 4 plus 4z? So we looked at 4 plus 4z over here, and I mean, let's look at some of the elements of 4 plus 4z. 4 plus 0 would just give you 4. Okay? 4 plus 4 would give us 8. Alright? So 4 minus 4 would give us 0. 4 plus 8, well, that would give us 12. 4 minus 8 would give us minus 4. Okay, and if we continue this process, right, I guess the question becomes this. If we really evaluated 4z and wrote out a couple of things, a couple of elements of 4z, of 4 plus 4z, sorry, does it make, because I mean, think about it, 4 is an element. Okay, so this was okay. 0 plus 4z was just 4z. So notice, I guess the question to ask is this. Right, so I mean, we're noticing some similarities. Every element of 4 plus 4z seems to also be an element of 0 plus 4z. Right? That's kind of clear. Every element there is a multiple of 4. In this case, it's kind of trivial, but let's think about it more carefully here, right? So, how to say it well is the question. Okay, fine. Let's notice something here. Well, 0 plus 4z contains all multiples of 4. Right? Everything we get is going to be a multiple of 4 because we're adding 0 to multiples of 4. What about 1 plus 4z? Well, 1 plus 4z contains what? Does it contain any multiples of 4? If we're getting multiples of 4 and adding 1 to them, right, can the answer that we get be divisible by 4? Well, the answer becomes no. Well, 4 does not divide 1. So 4 plus 1 does not divide 1. Sorry, 4 does not divide 1 plus 4. 4 does not divide 1 minus 4. 4 does not divide 1 plus 8. 4 does not divide 1 minus 8. In fact, the question becomes, can any element of 1 plus 4z be divisible by 4? Okay, so that's the question. Well, is this true? Can 4 divide any element of 1 plus 4z? Okay, well, all elements of, how would we determine this? Well, what are all elements of 1 plus 4z? Well, all elements of 1 plus 4z are really elements of the form, I mean, 1 plus 4z can be written as follows. It's a set of 1 plus 4n such that n is an element of the set of integers, right? We could rewrite it like that. It's this exact same thing. It's just, right now it's, right, here's would be 4 times 0, this would be 4 times 1, this would be 4 times 2, etc. And so that's kind of the definition of 1 plus 4z. Well, so can 4 divide any element of the form 1 plus 4n? Right? Now, of course, we notice that anytime we divide an element of the form 1 plus 4n by 4, we get a remainder of 1. Right? Remainder of 1. So no element of 4 can divide an element of, so this never happens. No element of 4 can divide an element of 1 plus 4z. But you see, 0 plus 4z consists of only elements divisible by 4. So, if all elements of 0 plus 4z are divisible by 4, but no element of 1 plus 4z is divisible by 4, is it ever possible for any element of 0 plus 4z to be an element of 1 plus 4z? This is all elements divisible by 4. Elements over here are not divisible by 4. In fact, 1 plus 4z could be thought of as the set of all elements which when divided by 4 gives us a remainder of 1. Okay? So given this information, can any element of 0 plus 4z ever equal to an element of 1 plus 4z? Right? Or, first of all, are these cosets even equal? Well, that's obviously not the case, right? So there are certain elements, actually every element in 1 plus 4z gives a remainder of 1 when divided by 4, but every element of 0 plus 4z gives a remainder of 0 when divided by 4. So, first of all, there is 0 plus 4z, the coset 0 plus 4z, right, and the coset 1 plus 4z, right, have no elements in common. Right? Completely disjoint, nothing in common. Okay. Another thing we notice, well, how about if we consider 2 plus 4z? Is 2 plus 4z, does 2 plus 4z have any element in common with 0 plus 4z or 1 plus 4z? Well, what is the set 0 plus 4z? 0 plus 4z is the set of all 2 plus 4j, right, such that j is an element of z. Right? That's by definition what it is. Well, another way of saying this is that 2 plus 4z, the coset 2 plus 4z is the set of all elements which when divided by 4 give us a remainder of 2. Right? If you get some element of 4 plus 2 plus 4z, maybe 2 plus 4j. If we try to divide this by 4, we get a remainder, right? Remainder of 2. So 2 plus 4z could be thought of as the set of all elements which when divided by 4 give us a remainder of 2. Alright, we just run out of time, so we'll have to continue this discussion of uh, these cosets of 4z of okay, so we'll continue this discussion in the next video about the exploration. But what have we done so far? This is important. So we're saying this: our main goal is to explore this idea that if G is finite, right, we have some finite group G, and we have some subgroup H of G. Is it true that the size of H, the cardinality of H divides the cardinality of G? Is this true? This is a question mark. And the way to figure out whether, the strategy we're using to figure out whether cardinality of H divides cardinality of G is to kind of figure out what's the relationship between the size of H and the size of G. Okay? And by looking at it, it's kind of hard. For some arbitrary group G and some arbitrary subgroup H, it's hard to tell what the relationship between the cardinality of H is and the cardinality of G is. It's hard to tell the relationship. However, what we do know is that we have these things we're calling cosets. These cosets always have the same size as H. While we may not be able to study the relationship between the cardinality of H, we may not be able to study the relationship between H and G directly. We may be able to study the relationship between the cosets and the group. In particular, we're exploring this bizarre idea. What if we came to the following conclusion, that if you got some group G, you can actually partition the group into these things we're going to call cosets. Right? Maybe we can do this. Right? Maybe we'll come to this conclusion that we can partition a group G into these cosets, like this, right? And maybe that coset right there, right? Maybe we can partition a group G into 4 cosets. And maybe, because I mean, we know that if GH always equals to H, the cardinality of GH always equals the cardinality of H, if we're able to partition G, we'd come to the following conclusion. By definition, I mean, by our previous arguments, cardinality of G1H, this coset, will equal the cardinality of H. Cardinality of the coset G2H will equal the cardinality of H. Cardinality of the coset G3H will equal the cardinality of H. Cardinality of the coset G4H would equal to the cardinality of H. The consequence of this would be that, well, G1H has the same cardinality as G2H. That's kind of clear, right? Because if they all have cardinality H, then all of them have the same cardinality. So right there would come to the following conclusion: all these cosets have the same cardinality. All right, so, and then, so maybe that will lead us to the following conclusion: if we get a group G and we can break it up like this into some elements of G come over here and there are cardinality of H of them, the other elements of G come into this box over here and the cardinality of H of them, the other elements of G come into the next box and the cardinality H of them, and the other elements of G come into this box and the cardinality H of them, maybe we can conclude that cardinality of H divides cardinality of G. Right? Maybe we can conclude this. But the way to see if these relationships even make sense is, we've decided to perform some exploration. We've gotten ourselves some group Z, okay, the group of integers under addition. We noticed that 4Z under addition actually happens to be a group as well. So the conclusion we've been able to draw is the following. Well, if we have some group Z, right, and we look at its subgroup 4Z under addition, and we think about the cosets, right? If we study the cosets of this, so those are elements of the form 0 plus 4z, 1 plus 4z, 2 plus 4z, etc., right, and so on and so forth, if we studied these cosets, would they tell us something about the relation between how many cosets there are and maybe, or maybe in this case actually the idea would be this, maybe do these cosets 0 plus 4z somehow partition, or if we look at, okay, so let's write this maybe a little clearer. We may have used up all the space. So this is really what our study of we're looking at here is like, maybe, okay, let's say we consider the group Z. Is it possible that maybe we can break it up into cosets of this form? 0 plus 4z, 0 plus 1 plus 4z, 2 plus 4z, say, and then maybe 3 plus 4z, right? Could we partition the group Z into these 4 cosets, right? Is that possible? And what would that mean? What sense does that make? So this is what we're exploring, and we'll continue the exploration of Z and its subgroup 4Z, and then we'll see if this can somehow lead us to some intuitions about what the relationship is between the cardinality of a group, of a subgroup of some original group, and whether maybe the cardinality of the subgroup must always divide the cardinality of the group. Otherwise, thanks a lot for listening to this, and hope the exploration was of interest to you. Otherwise, have a relentless week. Bye.